So why do people want to do high voltage transmission? Well, it's because it minimizes losses. Where do you get losses? Basically, you're sending current through wires. And the thing that you want to avoid there is basically you want to minimize the current. The more current you have, the more losses you're going to have. You can reduce that by getting bigger wires, but then you're spending more money to sort of build bigger wires. And you can also lose power to electromagnetic radiation. You have alternating currents, and they will radiate at that frequency. So that's where you'll lose power for transmission lines. But it's mainly the resistive heating, resistive losses that are problems. In transformers, you also have the resistive heating. You also have electromagnetic radiation, the frequency that you're generating. In transformers, you also have eddy currents. You have a big bunch of metal that you have currents going through, and it's possible that you can have smaller currents there that are not the currents that you're interested in. We call them eddy currents. And they help to sort of reduce the power. It's kind of how resistive braking will be used in cars. And hysteresis, you're basically sending flux in one direction and then another direction. The metal can become magnetized, and then you're basically spending energy to sort of remagnetize the metal. But here's sort of an example that illustrates the problem for why you want to have high voltage power lines. That let's say that you have a line that's operating at 100 volts, and you have let's say a 40 ohm power line. So you have a power line that you're starting with a power here that you're putting in, and you're sending it through 40 ohms. And then you want to dissipate some power. Here's the load you're trying to put power in. And let's say that this thing is operating at 100 volts. And we want to deliver 100 kilowatts of power. So this load here, we're going to say that the power is 100 kilowatts. So if we're operating at 100 volts, what current do we need to provide 100 kilowatts? 10 kilowatts. That's a question for you, gentlemen. Can you multiply by 10? Can you multiply by 100? Let's see, we want, power is equal to VI. And so this is like 100 volts times the current will be equal to 10,000 watts. So it's 10 to the fourth, that's 10 squared. So we're operating at a current of 100 amps. Good? Okay. So we have 100 amps going through this. Well, how much power are we going to dissipate in this 40 ohm resistance? There, we could say that the power that we dissipate will be, it's VI, or we could use I squared R, or V squared over R. But I squared R, we know that there's 100 amps flowing through this. So that would be 100 squared times the resistance, which would be 40. So this is going to be 10,000 times 40. So this is going to be 40,000 watts. 400,000 watts. 10,000 times. Yeah, so this is going to be 400,000 watts that we're dissipating here just to deliver 10,000 watts here. Okay? So that's how much we'd actually be dissipating. So this would be like 400 kilowatts that we're dissipating here. But suppose we were operating this this transmission line at 13,000 volts, which is kind of like a regional distribution voltage. Then how much would we be losing to the power line? Well, if we're operating at this at 13,000 volts, we're still providing 10 kilowatts, we can figure out the current from that. So the power would be, 13,000. Power is 10,000 watts, and that's going to be the voltage times the current. So that'll be 13,000 times the current. So this is 10 over 13,000. So that'll be something like 1 over, or 10 over 13, or something like 0.8 maybe? Somewhere around 0.8 amps. So we're drawing a lot less current. And then if we say, well, how much voltage, how much power would we dissipate in this 40 ohm resistor, or 40 ohms of resistance for this transmission line, we can say that, well, the power, again, we'll use I squared R. So that would be roughly 0.8 squared times 40. 0.8 squared is something like 0.6, maybe 0.64 times 40. So that would be somewhere around maybe 24, 25 watts. So the savings, so if we operate this thing at a high voltage, we're going to dissipate something like 25 watts, as opposed to the 400,000 watts that we're operating in the lower voltage. So that's really why people use high voltage power lines. That for the same resistance, you get a lot of, you do not lose as much to resistive power losses that you lose for lower voltages. Okay. Okay, so I got the 400 kilowatts right, and 24 watts. Okay, close enough. So that's about it. Is there anything else? So when you're near transmission lines, these are fields that are oscillating back and forth at 60 hertz. And you can certainly generate currents inside of your body, inside of your cells. And people have studied this and have seen it, that you can actually generate currents inside of cells, but there's no real evidence that it causes problems. Although there are studies that they've done of people who live in the vicinity of power lines, and it seems like childhood leukemia is one of the problems. That there's a slight increase in childhood leukemia of people who live near these power lines. But then we say, well, what kind of people live near power lines? Maybe there are other factors that come into play. So there are kind of studies that show that you definitely do this, but it's not ionizing radiation. It's nothing that really shows that there's a damaging problem. And I guess that's questions, comments?